All right, so we finished the first page of the worksheet in the last video. Moving on to the back of that for exercises 6 through 10. Starting with number 6, Mr. Wells says that his password is 7 digits followed by 7 letters and that neither the digits nor the letters are repeated. How many possible passwords are there? So we have 7 digits followed by 7 letters. This is what I was pointing out in the last video about problem 3, about how I tried to get funny with it and say, well, what if we do this? Makes it a much more difficult problem, as you'll probably see in the future. But this is not the case. We're going to pick 7 letters, and then we're going to pick, 7 digits, and then we're going to pick 7 letters. Okay, so we're told in the problem that neither of these two sets are allowed to be repeated. We also know it's a password. Passwords are one of the big things where order is going to be important. So no repetition, order matters is a permutation. So we're going to be picking 7 of each of these. So we are going to pick from the digits 10, 0 through 9 possible digits. We want order to matter, and we want 7 of those. For the letters, assuming the English alphabet, we have 26 available. We want order to matter. We're not repeating. We're taking another 7, and that's that. Number 7 says, in how many ways can first, second, and third place prizes be awarded in a math competition with 1,000 contestants? So we've got 1,000 people in a math contest. Let's maybe go when in doubt, write it out mode on this and say if I have 1,000 people available, I could put 1,000 possible people in first place, then only have 999. It's kind of implied here that the repetition is not allowed. I can't have somebody win first and second place. It's not stated specifically in the problem, but this is one of those times where we have to infer just by common sense that we're not going to be repeating anybody. Okay. So we have first, second, and third place. We want to think, does the order of this problem matter? Because if we're doing this formulaically, right now we've implied that the order matters. Whenever I use fundamental counting and I'm drawing elements from the same set, I'm implying the order that I multiplied them in mattered. And does it matter here? Well, if I have the same 3 people, and I give you first, you second, and you third, that's one way to arrange it. But then again, I could have the same 3 people and say, no, you're actually coming in second, you're first, and you're third. That's the same 3 people in a different arrangement. So order here does matter. So we could more efficiently write this as 1,000 P3. So again, efficiency counts, pretty small numbers there. If it was, we were assigning first through 50th place, we don't want to type that much out. 1,000 P50 would be a much better way to go, and might possibly overload our calculator. Anyway, number 8, music recital problem. We saw this in the most recent textbook exercise taken straight from. Here we have a music recital with 5 girls and 4 boys, and each musician will perform only once. In how many ways can we arrange the program if all of the girls must perform first? Let's write it all out. So I have 9 people consisting of 5 girls, 4 boys. In this arrangement, we want all of the girls to go first, meaning all the boys will go after that. So I have 5 possible girls to go first. So we're going to run down just like that. Now we've arranged all the girls. Likewise, arrange all the boys. In terms of efficiency, let's just call that 5 factorial. Just call that 4 factorial. So let's show 3 different ways to do this. For one thing, we can multiply all those red numbers together. For another, we can multiply those 2 things together. And this is still equal to, whenever you have a factorial involved, you could just use a permutation if you really like that. So we've got 3 different ways to actually calculate this arrangement. I would probably go with the green myself. Do as you please. Number 9, in how many ways can 5 students be seated in a row of 5 chairs if one particular student insists on sitting in the middle? Number 9, just to illustrate this. I would hope at this point that you're maybe getting close to where you can look at a problem like this and say 4 factorial. If not, look at writing it out. If we have one person in this group that insists on sitting in the middle, we're not arranging that seat or that person. So that person is going to be there. They may as well not even be a part of this. And we could just say, really, I'm arranging 4 people in 4 seats. But if you like the visual of this, take it. I've got 4, 3, 2, misspelled 1 there. 1 way there. Of course, this is, for efficiency's sake, 4 factorial. Okay, finish this off with number 10. Number 10 says that the Missouri Powerball Lottery has players choose 5 distinct integers from 1 to 69 inclusive, and a single integer, the Powerball, from 1 through 26. Unstated, but that's also inclusive. A player wins the jackpot if all 6 of the numbers they choose match the drawing. The order that the numbers are picked, drawn in, is irrelevant. How many tickets would you have to buy to be sure that you win the jackpot? So first, let's call attention to a couple things, because this is a longer reading comprehension issue. So for one thing, we know that we're inclusively looking at ranges of 2 different sets of numbers, 1 through 69 for the first numbers, 1 through 26 for the Powerball. For those first 5 numbers, it says 5 distinct integers. So for one thing, we know we're dealing with integer values. And we also know that distinct means different. So they're all unique, so no repetition. So we're going to be thinking about permutations or combinations. Later on in the problem, we see that the order that the numbers are picked in is irrelevant. So if you've ever seen a lottery drawing before, they'd have like a big machine bouncing around a bunch of ping pong balls that have numbers on them, and it sucks them up, and generally speaking, the numbers don't come up in a numerical order. The order that they come up in is irrelevant, because once it's over, they'll then display, here's tonight's winning numbers, and they'll just conventionally do them in numeric order. So the order that the numbers are picked in doesn't matter. So, no repetition, order doesn't matter, it's going to be a combination. So let's look at a 2-part task here. One where we're going to pick 5 numbers. Important to point out, just because we do this so often, we are dealing with numbers in this problem, integers, not digits, coming from the set 0 through 69. And then here we're going to pick our Powerball number. And this number is going to come from the set 1 through 26. Because they're being drawn from different sets, remember we said no repetition, but the no repetition is coming in here in the first 5 digits. Here, say that one of these numbers comes up as 11. Because I have a whole other set of digits here that I'm drawing from, this number could also be 11. So I can have repetition between the 2 tasks, just not in this first group. Important to distinguish. Okay, so 5 numbers, no repetition, order doesn't matter, combination, 69, C5. The Powerball. Let's think about this for a second. On one hand, you might say, well, I'm only picking one of those numbers, and you said all the stuff about it doesn't matter, blah, blah, blah. So 26C1 might be one way to think about it. A more efficient way to think about it in terms of saving time and, energy, punching buttons on your calculator. 26C1, to write it again while I say this, 26C1 is the number of subsets that have one element taken from a set of 26 elements. So we know, and we've seen this before, if we wrote all this out, say these are the numbers 1 through 26, all those subsets would be 1, the set containing 1, the set containing 2, 3, 4, 5. So this is actually just 26. It's a better way to probably think about it. I definitely don't want to have to go and jump into those menus and get the combinations if I don't have to. So there's 6 through 11. No, it's not. It's 6 through 10. Let's do 11. A professor teaches 2 classes, one of 60 students and one of 40 students. 5% of the students in each class are to receive a grade of A. And how many different ways can the A's be distributed? First off, we're going to think about some percentages. I think I've got enough room to do this right down here. So on one hand, I need to think about 5% of 60 and 5% of 40. Now, in terms of how comfortable you are with doing percentages in your head, I would think of it this way. What's 10% of 60? 6. What's half of that? Because 5 is half of 10. So if 6 is 10% of 60, 3 is 5% of 60. And likewise, 2 is 5% of 40. Now, we've got 60 students in the first class. 3 of these students are going to be getting A's in the class. Now, I can't tell the difference between one A and another. If that student, and that student all get A's, it doesn't matter which order I gave them in. Now, if it was like an A, A plus, A minus, now we can tell the difference. It's like first, second, and third place, so the order would matter. But in this case, the order is not going to matter because we can't tell the difference between the different A's. So we'll say 60, C3, getting 5% of the 60 students, times, we still need to think about this as fundamental counting because we could choose the same people here and then different people here, creating more and more arrangements. Sorry, arrangement's a bad word. More and more sets of people. And then over here, 40C2. Okay. So there is your 6 through 11. And we'll be right back.